Good morning, everybody. Good morning. Good morning. I'd like to welcome everyone to the CREOL Symposium, where today we have the absolute honor to receive a lecture from the eminent Dr. William Phillips of NIST, who, as we all know, won the 1997 Nobel Prize in Physics for laser cooling. I would like to share with you a very, before you can do that, please, for the students, I encourage you all to visit the Wikipedia page. His list of awards are absolutely phenomenal, ranging from the Samuel Wesley Stratton Award, the Fleming Award, the Gold Medal from Department of Commerce, the American Academy of Arts and Science, the Michelson Medal, et cetera, et cetera, et cetera. The interesting thing that we also like to note is the academic lineage. And Dr. Phillips can actually trace his lineage back to Albert Einstein, including Israel Isidore Rabi, Norman Ramsey, Dan Kleppner, who I think has birthed 3 Nobel Prize winners, Carl Wyman, Eric Cornell, and Bill Phillips. You can fill in those details.
And Wolfgang Ketterle is probably adjacent as well. So.
But I would like to share with you a little short story. The process for getting Dr. Phillips here started nearly 30 years ago. So it was a Tuesday night, October 14th, 1997, and we're at the OSA's annual meeting, and we're at either president's reception or the chair's reception. MJ might have been there. I know that Eric was there for sure. And we're chatting up with Bill, and Bill is telling us about all of the different interesting things that he was doing with outreach, working with science centers and teaching the public about science. And so Wednesday morning, I get up early to go to the OSA board meetings. I turn on the TV. It's 6:10 in the morning. Nobel Prize in Physics was announced.
You spent the time about he had agreed to come visit.
Correct. So I was talking to Bill, and he says, "Oh, gee, I should come down to visit you guys in CREOL." Here we go. So anyway, the next morning we wake up, we hear that he has won the Nobel Prize, and I'm thinking, he's not. So I've served on many committees with Bill, UPAP being one of them. But last year I was giving an interview webinar with the National Society of Black Physicists, and after everything was over, the moderator says, "There's a question in the chat from a William Phillips." So I said, before I answer the question, may I ask, is this the William Phillips of NIST and the Nobel Prize? The chat window open and all the little words. Yes. So I relate the story to the crowd, and then a few hours later, which was actually on February 14th, almost a year ago, exactly to the day, where Bill replies to say, "Hey, Peter, it was good seeing you. I think it's time." So for the graduate students, perseverance. So at this point, let's turn the floor over to them.
Well, thanks very much. So please, since we don't have local amplification, I will try to keep my voice up. So those people in the back, I'm relying on you. If I drop my voice too much, or if turning to the screen doesn't work, I want you to yell out louder or something along those lines so that I keep everybody in the back. When I was a graduate student, I noticed that all the famous professors would sit in the front row, and I thought it was because they were so famous. But now that I'm their age, I realize it's so they can hear and see. But another point about the October 1997 was that there was some discussion. We knew the Nobel Prizes were going to be announced the next day. And we were thinking, wow, wouldn't it be great if the Bose-Einstein condensate people got the Nobel Prize? Because some of them are right here at this meeting. This will be fantastic for the meeting. No one suggested me as being a possibility for that. So, there are surprises. Anyway, let's talk about the metric system. In recent times, the metric system has changed in dramatic ways, and that's what I'm going to be talking about. Well, you've already heard. I'm from NIST. This change in the metric system is very quantum, and I'm going to emphasize that as well. And I want to emphasize also that I'm from a place called the Joint Quantum Institute. So quantum is our middle name. And it's joint between NIST and the University of Maryland. And as part of that, we have the laser cooling and trapping group. Ian Spielman is the leader of that, and these other people. Gretchen Campbell used to be the leader of that, but she left NIST and is at the University of Maryland, which means that she didn't even change her office. So that has worked out very nicely. And these other people who are part of the group are a pleasure for me to interact with. I also, speaking of IUPAP, am representing IUPAP. IUPAP is, so how many people have even heard of IUPAP? Okay, that's like 2% of this audience. So IUPAP is the International Union of Pure and Applied Physics, and it's an international organization that with representatives from all over on all sorts of committees that do practical things like promote the metric system. And in fact, IUPAP was one of the promoters of creating what is now called the International System of Units, the Système International, or SI, in 1960. So, and I'm part of that still as a kind of a supernumerary member of the committee, going around giving talks like this to promote the new SI, the new quantum metric system. Now, please think about questions, because at the end, when it's time for questions, everybody who asks a question will get a prize. And any question is fine, except the question, what is the prize? You'll find out. Okay. So I also want to mention that this talk is very much in line with the recently completed International Year of Quantum Science and Technology. But the fact is, we continue to celebrate, because 100 years ago was the Schrödinger equation, whereas 101 years ago was Heisenberg's formulation, from which we didn't get Heisenberg's equation of motion until Dirac read the paper, which he did in proof form. Somehow he got his hands on the galley proofs of Heisenberg's paper and realized, oh, wow, this looks like Poisson brackets. And he figured out the Heisenberg equation of motion was Dirac as a graduate student. So you graduate students, get to work. Okay, so back to the revolutionary changes of the metric system. Well, the French Revolution was the event that, in a sense, brought us the metric system in the first place. The French revolutionaries wanted a new system of measurement that would represent the principles of the revolution of internationality and equality. And what I'm here to tell you is that on the 20th of May, 2019, which doesn't seem so long ago to me, which I'm sure you all recognize as being World Metrology Day, we had what I consider to be the biggest revolution in measurement since the French Revolution. Okay, and the nature of that revolution is to change the definitions of the base units of the SI. So the International System of Units, our metric system, has what are called base units in which everything else can be expressed: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. And the thing that is new is that now every one of these units are defined by fixing the value of constants of nature. Fixing the values of constants of nature. Now, how this can come about, I'm going to illustrate for you by describing something for which this has been true for some time, namely time itself. And so I'm going to give you, with apologies to the late, great Stephen Hawking, my version of a brief history of time. So since people have had seconds, a second was a certain fraction of a day. Well, you know what it is, 1/24 times 60 times 60, that's what a second is. Now the question is, what is a day? Now, it may be obvious, but the fact is that the solar day changes by a whole lot during the year because of the ellipticity of the Earth's orbit and the tilt of the axis. So it's the mean solar day is the thing that was defining what a second was. But since around the turn of the century, that is not the last one, but the one before that, we've known that the mean solar day is changing for any number of reasons. The tides act as a kind of a friction force on the Earth. Every time there's an earthquake or a change in ocean currents, that means that the angular momentum or the moment of inertia of the Earth is changing, and all these things can be determined. Clocks were in fact good enough to see this by around 1900. Clocks at, guess where? The National Bureau of Standards, which became the National Institute of Standards and Technology, my institution. Here's the first atomic clock, again at the National Bureau of Standards. The only trouble with this atomic clock is that it's not atomic. It's actually an ammonia molecule, but same idea. 1949. This clock is a lot better than the Earth. And with a clock like this, you can easily tell that the Earth's rotation is changing. Here's a perhaps more relevant clock. This is the first cesium atomic clock based on ideas from I.I. Rabi and Norman Ramsey, operating in 1955. The basic idea, the very oversimplified version, is that you've got a cesium atom here, illustrated by a nucleus and a valence electron. And the idea is you shine in microwaves at about 9.2 gigahertz. That's the frequency that's resonant with a spin flip of the electron relative to the nucleus. And I'm telling all kinds of oversimplified lies here. So feel free to ask about that at the end. So you just tune your microwaves until it's the right frequency that's making the electron flip, and then you know that frequency is this hyperfine frequency, and it's defined to be this. So in 1967 or so, the second was redefined from an astronomical definition to basically defining what is this spin flip frequency in cesium. And then you make a clock by tuning your microwaves until it makes the spin flip. So that's the actual official definition of the second in 1967. And since that time, well, since before the time of the redefinition, the clocks have gotten better. So this is the fractional uncertainty, the systematic error in determining that clock frequency as a function of time, leading up to about 1990. But by 1990, the performance of these clocks was stalled, mainly because of the fact that the atoms are thermal and moving with a velocity of more than 100 meters per second. And it's just not that easy, for any number of reasons, to observe the ticking frequency of something that's moving at over 100 meters per second. As you can imagine, there's Doppler shifts. There's also the fact that it's going to fly out of your apparatus in a finite amount of time. So all these things tended to conspire to limit the ability of these clocks to keep time. And the best of these clocks are NIST, of course. But everybody in the world was keeping time this way. And so in response to that, my own group started to work on laser cooling, trying to make these things go slower. And eventually, and that's a whole other colloquium, we got the cesium atoms, so instead of going at over 100 meters per second, they were going at less than a centimeter per second, and that made a huge difference and allowed the performance of these clocks to continue to improve with time to the level of a few parts in 10 to the 16, which is where they are now. And here is a picture of such a clock. So Don Meekhoff and Steve Jeffords cool cesium atoms down here, launch them up in a vacuum. They come back down after about a second. And that long time, as well as the absence of Doppler shifts and various things that are related to Doppler shifts, like distributed cavity phase shift, are so small that these things are now at a few parts in 10 to the 16th, the most accurately measured anything in modern times. So I want to emphasize the key concept here. We go from something that's totally arbitrary, namely the rotation of the Earth. I mean, the only thing that's special about the Earth is we live on it, right? And nothing keeps that rotation stable. And we change that to the properties of an atom, the properties of an atom that we believe are themselves completely stable. Now, we weren't the first, by we, I mean the present metrological community, we weren't the first to think about this. Kelvin and Maxwell, back in the 19th century, advised that if we wanted to have standards that could really meet the test of time, that it should be based on the properties of atoms. Now think about this. This was at a time when most people didn't even believe in atoms. And yet Kelvin and Maxwell are saying that the properties of atoms are absolutely uniform, that every atom which is available in infinite numbers made by God, that they're all exactly the same. How did they know that? I mean, now we understand quantum mechanically why these things have to be absolutely identical. But this is before quantum mechanics and before people even believed in atoms, and yet they thought that this would be a good way of creating a standard of time, and now that's the case. Okay, so now I want to tell you another story. It's even better. I'm calling it a short history of length. Now, time was important in ancient times, but length was really important because length came into commerce and construction. And the earliest length standards were based on the human body. I mean, what could be easier? A fathom is your wingspan. A foot is a foot. And the great thing about this is you've always got the standard with you. On the other hand, if you're buying fabric in the marketplace from a short fabric merchant, you may not get as much cloth as you thought you wanted, and so this was a problem. Well, one of the ways in which the problem was addressed was to make the length standard based on the body of a particular person, typically the monarch. And this goes back to ancient Egypt, where the length of the pharaoh's forearm became the standard for the royal cubit, which was the standard of length. And that standard of length was used to do things like build the pyramids. Now, the pharaoh wasn't always around. So guess what? They made an artifact. This stone rod was the realization of the length of the pharaoh's forearm. I think there was a palm added to it, but it doesn't matter. And then they had working standards that they would use out in the field that were made of wood. And I love how serious these people are about metrology, because it was mandated on pain of death that you would calibrate your wooden standard against the stone one at least once a month. So these people really were serious, and as a result, the pyramids were pretty good. The baselines are consistent to a tiny fraction of a percent. They're square to 12 arc seconds. These were well-made things because they took metrology seriously. And artifacts, I mean, this is, as it turns out, a very modern approach to things. These artifacts were all over Europe, for example, in medieval and later times. Here is an example of the wife of a metrologist who's measuring her fathom against the standard fathom in Regensburg. As you can see, this would be a good place to buy fabric, because a fathom is pretty long. But if you were to go to other nearby towns, you would encounter a different set of standards. So all over Europe, you had all these different standards, sometimes with different names, sometimes with the same name, just with different values. And this was what the French revolutionaries wanted to change. And so they decided that in the interests of universality, that they would use the Earth itself as the standard of length, and a meter, this new unit of length was defined to be 1/10,000,000th of the distance between the pole and the equator along a meridian that goes through Paris, just to make sure it was completely international. And uh, the philosophy was that the meter was going to be then the measure of all things. It's going to be the base of measurement, and would be something that would be good for all people for all times. And this coin was struck to commemorate that idea. And you see that there's a sort of a mythological creature with some dividers measuring the Earth. And that's exactly what they did. They sent out surveyors, really astronomers, to measure the length of the meridian between Barcelona and Dunkirk. And they took a couple of years to do that. They kept being thrown in jail because it was during the Napoleonic Wars, and they show up in town with a bunch of scientific apparatus and want the highest spot, to do their observations so they could triangulate the distance along the meridian. And but after some years, they came back with a measurement of the meter, this new meter, in terms of the old system of units. But of course, it took years to do this. And so what did the French Academy do? They made an artifact. So this is a rod of a platinum rod that corresponds to the meter that had been measured by, what were their names? Delambre and Mequin, who led the expeditions north and south of Paris to measure the meter. So this is the meter of the archives. This became the standard of length for France. A few decades later, the countries of the world gathered to discuss and to ratify the Treaty of the Meter. And one of the things they did was they made a new meter, now made out of platinum iridium and a little bit more intelligently designed, and to be made the same length as the meter of the archives. And this became the length standard for the entire world from 1875 on until the next change. So kind of interesting. Well, for one thing, last year is the 150th anniversary. And so we had celebrations in Paris with the International Bureau of Weights and Measures, and that was lovely. But one of the things that's interesting is that about the same time that the international prototype meter was made and agreed upon by all the countries in the world. I think there were 17 countries who were original signers of the Convention du Mètre, and everybody who was an original signer contributed money to set up the International Bureau of Weights and Measures, and they got copies of the meter. And so, and then they agreed, of course, that the metric system would be their standard. The United States was one of the original signers. Okay? So, but around that time, we're talking about late 19th century. Well, we know what was happening in the world of physics with respect to light. People had discovered that light was a wave, and using things like interferometers, this is a cartoon of a Michelson interferometer, you could measure displacements that were a fraction of a wavelength being about a half of a micron, half of a millionth of a meter, and you could measure displacements that were smaller than that. The meter was defined as being the distance between two scratches on this bar, and those scratches were about 20 microns wide. So you now have a technology that can measure things to a fraction of a micron, a definition that is 20 microns uncertain. Well, clever people could figure out where the center of the scratch was, but you see what the problem is. So people started to use light as a kind of a de facto standard that was not really the legal standard, but was something that was used because its technology was so much better than the actual legal definition of what a meter was. So in 1960, they finally got around to changing that. They said in 1960 that the meter was a certain number of wavelengths of the orange light that comes out of a krypton lamp. 1960. the year the laser was invented. Okay, so it didn't take very long before the light from a laser was understood to be so much more pure than light from a krypton lamp that people started to use the laser as a de facto standard of length. Excuse me. It's just like what happened with the difference between the international prototype meter and the interferometers with lamps. We now had a technology, namely lasers. I'm so sorry. Just a little dry, I guess, and so I think that a cough drop might. Yeah, I got some water here too, but the trouble with water is that it temporarily solves the problem. But okay, great. So people were using these lasers. This is an iodine stabilized helium neon laser. So it's a red laser that is stabilized to a particular transition in molecular iodine. And everybody was using this as a de facto standard. So the obvious thing to do would be to redefine the meter in terms of this kind of laser. That would have been the obvious thing to do. Fortunately, people chose instead to do the brilliant thing instead of the obvious thing. And the brilliant thing was to define the speed of light. So why does this define what a meter is? Well, the new definition of the meter is the length of path traveled by light in a time interval of some fraction of a second. That denominator is obviously, by definition, the speed of light in meters per second. So that means this definition defines the speed of light. Now, the beauty of this is that this relationship between the wavelength of light, its frequency, and the speed of light is universal. So it doesn't matter what kind of light, what kind of laser I have, if I can measure its frequency and I've defined the speed of light, I immediately know its wavelength, and I've got a ruler that can measure length. And by 1983, people had learned how to measure the frequency of light. And so it was time to change the definition. Today, we have so much better ways of measuring the frequency of light. We have so much better lasers. And the beauty of this is that all of that improvement, some of which was done by these people who got a Nobel Prize in 2010, for frequency combs and better lasers. All those improvements didn't require a change in the definition of the meter because of this beautiful choice of defining the meter by defining the speed of light. So now this is even better than what happened with time. We go from an artifact to an atomic standard, krypton, to a universal constant, the speed of light, as the way of defining what we mean by a meter. And so, as long as we use the same kinds of methods for measuring length, we should never have to change this definition. So now, what I'm telling you is that on the 20th of May, 2019, we have instituted into the International System of Units this same beauty that we had for the definition of the meter into the definition of the kilogram and, for that matter, the ampere, the Kelvin, and the mole. And the main story is the kilogram, so that's what I'm going to tell you about now. And probably the thing that was in the news was that the kilogram was being dethroned, as people often said. So why did we have to make this change, and how was it done? So we're now going to have a light history of mass. So not surprisingly, in the ancient world, mass was based on artifacts. So this set of polished stones were used in ancient Babylonia to act as the standards of mass. I forget which one, but one of these things is a shekel, a word you might have heard. And And it had the same kind of problem that all of these artifact standards had, that if you go from one place to another, you're going to have a different set of standards. So the French revolutionaries knew what to do. Use the meter to define a unit of volume called a liter, and make the mass of water that fits into a volume of a liter, make that this new mass unit, the kilogram. And so this is great because, you know, everybody's got water, and we know what the meter is. Well, we have an artifact. We know what the meter is, but the point is that we have a standard based on the meter and based on something fundamental in nature, namely water. Trouble was that, as good as that sounds, it's not that easy to put together a liter of water at the level that corresponds to the kind of precision with which things could be weighed. And so, guess what? They made an artifact. They made a right circular cylinder of platinum. Why platinum? Because it's one of the densest of all of the metals, and that way you don't have to worry about the buoyancy correction from the buoyancy of the air, which is an important feature. And even, you know, back in 1875, actually this was 1799, they understood this very well. So here it is. That is the kilogram of the archives. What a thrill to hold that in my hands. This was deposited in the archives of France along with the meter of the archives in 1799. Okay, and there I am holding the box that holds that platinum cylinder that was made as closely as possible to the mass of a liter of water. And now it becomes the standard for all of France. As with the meter, a few decades later, the international community agreed upon the metric system, and a new artifact kilogram was made, this time out of platinum iridium, that became the international prototype kilogram. And there it is. It's under 3 glass domes and is only taken out once every 20 or 30 years to compare it to other similarly made artifacts. So this is the definition of the kilogram. Up until 2019, this was what we meant by a kilogram. It's the mass of the international prototype kilogram. What could be simpler? But think about this. We are now in the 21st century. The unit of mass is an artifact. It was made in the 19th century based on an artifact that was made in the 18th century. This is such a scandalous idea that a newspaper comic strip made fun of it. So in this comic strip, a little girl who is inside this institutionalist-looking school asks her science teacher, am I not right that the meter has been redefined in terms of the speed of light? Yes, because the science teacher says, because the old definition based on the size of the Earth wasn't very good. And isn't it also true that we've redefined the second that used to be based on the rotation of the Earth in terms of the cesium atom? And the science teacher says, yes, that's right, very good. So why haven't we changed the definition of the kilogram, she says. That the official definition is still the mass of the international prototype kilogram, an actual lump of stuff that is stored somewhere. That somewhere, by the way, is Sèvres, which is just outside of Paris. I've been there. I've seen the kilogram with my own eyes. And the teacher says, that's so unscientific. She says, what? Exactly. What if someone sneaked in and shaved off a piece of the kilogram? Then we find out that, of course, her only motivation was to bedevil her teacher, which, of course, is the job of students. So nobody sneaks in and shaves off a piece of the kilogram, but it appears that its mass is changing nevertheless. Here is a plot of the mass of a number of different kilograms relative to the international prototype kilogram, measured at only a few times in history, because as I said, it only comes out, once every 20 or 30 years. So as you can see, most of the kilograms of the world are getting heavier compared to the international prototype kilogram. It doesn't take too much imagination to think that maybe it's the international prototype kilogram that's getting lighter, and that all the other ones are changing relative to each other as well. And all these kilograms were ostensibly identical when they were made. Okay, so obviously there's something wrong. The kilogram is changing, but of course, legally the kilogram cannot change because it is the definition of what we mean by a kilogram, is the international prototype kilogram. So this is intolerable, right? You have a standard of mass that is clearly not stable, and what do? And the answer is, we change the definition, and we want to change the definition by using the same philosophy that we used with the meter, namely define a fundamental constant of nature. So what is that fundamental constant going to be? Well, I want to remind you of what is surely the most famous equation in all of history, E equals mc squared. What does it mean? The total energy of an object is equal to its mass times the square of the speed of light for an object at rest. Now, an not equally famous, but also pretty famous equation is this, that the energy of a photon is equal to Planck's constant times the frequency of the light. Now let's just willy-nilly combine these two equations and solve for the mass. So it says the mass is equal to Planck's constant times the frequency divided by c squared. So what does that mean? If I had, for example, some matter, let's say an atomic nucleus, and it emits a gamma ray whose frequency I can measure. And by the way, we now have such a system where we can measure the frequency of the gamma ray coming from thorium-229, and we can, using frequency metrology, so it's amazing what's become of this, because this was just sort of a thought experiment before. You measure the frequency of that photon coming out, you've already defined the speed of light, you've newly defined the Planck's constant. That tells you what the mass difference is in the nucleus. Now, this kind of experiment can be done, but it's not really good enough as a replacement for the platinum iridium kilogram, but it gives you an idea of how it is, why it is that if you define Planck's constant, you can define mass. So that's what, okay, so what we're going to do instead is we're going to use a procedure to measure the mass of an atom in kilograms using this technique, and then multiply it up to get to a kilogram size. So this is where, for the first time, well, maybe not the first time, the second time in this talk, where laser cooling comes in. So we start with a gas of rubidium atoms that have been laser cooled down to a few microkelvins, and we shine in light, and we know what the frequency of that light is, and that light promotes the atom from its ground state to its excited state. That's where the energy goes. But the momentum of the photon, which we also know precisely, goes into kicking the atom with a certain velocity that we call the recoil velocity. So we can measure that using techniques involving atom interferometry, which I'm not going to go into right now. And we can measure that velocity very well and solve for the mass. We found that the mass of the atom is equal to Planck's constant divided by that velocity times the wavelength of the light, which are all things that we can measure really well. So now we know what the mass of a rubidium atom is. People have done mass comparisons of atoms over the years using mass spectrometry and trapping of various nuclei, various charged ions. So we know the ratios of masses very well. So that means that you can go from the mass, remember this is the mass in kilograms, not in atomic mass units, which is relative to carbon, but in kilograms, okay? So you can, we now know what the ratio is. We have from previous measurements, we know what the ratio is of the mass of, say, silicon to rubidium. So then you make a perfect crystal of silicon and people know how to do that because of the semiconductor industry. And you machine it and polish it and make the roundest thing that has ever been made on Earth. If this thing were as big as the Earth, the tallest mountain would be like a molehill, okay? That's how round this thing is. And then you measure it, and you measure the spacing, the lattice spacing of the crystal. It's a single crystal. It's also isotopically pure. And that means you know how many silicon atoms are in here because you know what the dimensions are, you know what the lattice constant is, you know how many silicon atoms there are, and you know the mass of a silicon atom, you know the mass of that thing. And this is not like an artifact, okay? This is something that anybody could reproduce from scratch. You wouldn't have to know anything about an artifact to try to reproduce that. You could describe to Martians how to make this kind of a kilogram, and they could do it. So, blah, blah, blah. Now, one of the beautiful things about this new definition of the kilogram, defining Planck's constant, is it doesn't tell you how to do it. So I've just told you one way of doing it, but there's another way invented by this guy, which I don't have time to tell you about, in which you measure the forces between current-carrying wires, and because you measure the current in terms of a voltage using the Josephson effect, and in terms of a resistance using the quantum Hall effect, you've got Planck's constant in there, and you can have another way of getting to the kilogram, and this is what we do at NIST. This is a machine called a Kibble balance, after Brian Kibble, who came up with the idea, and it realizes the kilogram to about 10 to the minus 8, which is about the level at which dirt effects change the platinum kilograms from one time to another. So these are the serious metrologists who have done this. They are so serious about their metrology that they have tattooed the values of the fundamental constants that are related to this new revolution in metrology on their forearms. And now some of the people actually used henna, and some people actually got real tattoos. I think you can tell which are which. But still, I think this represents a kind of seriousness about metrology that goes back to the tradition of the ancient Egyptians. So all over the world, people have been measuring Planck's constant, because until you actually make the change, when you do this experiment, what you're doing is measuring Planck's constant, okay? So then when you're done, you're going to define Planck's constant, and all these experiments will be realizing the kilogram. So people are doing one thing or another, the Kibble balance or the silicon sphere, all over the world, and when everybody agreed to within a few parts in 10 to the 8th, then they made the change. Now, I'm not sure. I should have checked this out. I forgot that we had. I've got a video that was shown in Paris in November when the International Conference on Weights and Measures officially agreed that we were going to make this change. The change didn't happen until May, the following May, but they showed this video, and I'm hoping that the sound is enough that you'll be able to hear it, even though I don't have amplification. So let's find out.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community. At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. Facts.
We did it. Ce l'abbiamo fatta. L'ologrammi.
Lei si è bonita. Biz bunu жасады. Det är sånt svårt. Vi gör det. Vi gjorde det. Vi smartade oss in i det. Dokazali sme to. Congratulations. Stämmer. Felicitazioni.
Guarda il top. Congratulazioni. State lavorisce. Lama. Successo. Parabéns.
Ongela. Momento.
Anguida.
Onneksi olkoon. Magnus.
Kapai.
Aiko.
Félicitations. Congratulations.
Well, I still get choked up when I see that video. To see all these nations, 60 nations of the world, unanimously agreed to make this change, it really gives you some hope that maybe other things can be done with that same spirit of internationalism. Let's see. Okay, maybe we in fact have enough time to talk about this. So it's not just the kilogram that got changed in 2019. The ampere. So it used to be, and you probably remember this from your high school days, that the ampere was that current which, when put through two infinitely long straight wires, 1 meter apart, would produce a force of 2 times 10 to the minus 7 newtons. Now, that definition, by the way, is equivalent to defining the magnetic permeability of free space to be 4 pi times 10 to the minus 7, whatever it is, newtons per ampere squared. Although that often is not emphasized. So we already had a definition of the ampere that was based on defining a fundamental constant. It just wasn't the easiest thing to use. The new definition defines the charge of the electron. So the new definition of the ampere is just a certain number of electrons per second. Isn't that wonderful? Now, we're not yet at the level that we can count the electrons well enough that that becomes the way in which we realize the definition. The way in which we realize the definition is by using the Josephson effect and the quantum Hall effect, but it amounts to the same thing. And so for example, this cartoon sort of illustrates that if I put current through some resistor, I measure its voltage, and the Josephson effect tells me that the voltage is proportional to H over 2E, and the resistor is proportional to the quantum Hall resistance, which is H over E squared, and so you end up with a current that's proportional to the charge of the electron. Great. Now, let's see, do we have time? Sure, let's just do it. There's a dirty little secret about electrical measurements that almost nobody, including physicists, know. And that is, from very early times, early in the 20th century or late in the 19th century, we have had two different systems of electrical measurements. One was the SI, the thing we've been talking about. The trouble is that the SI definition of the ampere is so difficult to use, measuring forces between wires, that people insisted on having an easier way of doing it. And that easier way was to wind a wire-wound resistor to be as close to the SI ohm as you could make it, and make that your legal ohm. To get a battery, a thing called a standard cell, measure its voltage relative to the SI volt as well as you could, and make that your legal volt. So every country had a bank of resistors kept in an oil bath at constant temperature, and a bank of standard cells kept in some kind of a constant temperature enclosure. And those things were the legally defined volt and ohm for that country, and every country had a different set. And I was actually hired by NIST in 1978 to measure the ratio of the US legal ampere relative to the SI ampere. That's why I went to NIST, to measure that quantity. And now, because, okay, so what happened was, historically was, that eventually along comes the Josephson effect, and people changed the legal definition of the volt to be based on the Josephson effect, still not the SI, okay? And then when the quantum Hall effect came along, the whole world changed their definition at the same time to correspond to a realization of the ohm using the quantum Hall effect, and again, not the SI. So from 1900 or so, we had two different sets of units, different in every country. By 1990, we had two different sets of units, the same in every country, okay? And now, we only have one set of units, because if you define E and H, then you define 2E over H and H over E squared. So that dirty little secret has gone away. We've become honest metrologists finally, and don't have two sets of books for our, okay, so blah, blah, blah. Right, the mole and the Kelvin. So it used to be that the mole was the number of entities that corresponded to the number of carbon-12 atoms in 12 grams of carbon-12. You remember that, right? Now the mole is just a number. So based on all of these measurements, including the silicon spheres, we've been able to redefine the Avogadro constant. Well, to fix the Avogadro constant. And that's what we mean by a mole. The Kelvin used to be 1 over 273.16 of the triple point of water. And now it's defined by defining the Boltzmann constant. And if you multiply the Boltzmann constant times Avogadro's number, you get the universal gas constant. And that's still the way in which we realize the Kelvin is using gas thermometers, but we're very close to being able to measure the velocity distribution of the atoms in a gas, which we know, once we know what Boltzmann's constant is, we know what that distribution is in absolute velocity units, and use that as a way of measuring temperature. So the whole system has become very atomic, very quantum in its nature, because we're now talking about temperature at the atomic level as having to do with the kinetic energy, the thermokinetic energy at the atomic level. We're talking about the Avogadro number as counting atoms. So we've really come to this situation that was sought after by the French revolutionaries of having something that would be good for all times and for all people. The liberally leading the people in this amazing painting can symbolize the idea that we're now free from artifact standards, and we're free from a double standard of electrical measurements. So all the base units are now defined by fixing the values of constants of nature, and we seem to have finally realized the dream of the French revolutionaries to make something that's good à tous les temps, à tous les peuples, as illustrated by this old coin, except it seems for time itself, because time is still defined in terms of the cesium transition, and guess what? We've got better atoms now. Because of the fact that we can measure optical frequencies, we can now make atomic clocks that use optical frequencies, and these things in red illustrate how, over time, the optical frequency standards have improved. So they are now down at the part 10 to the 18 level for optical standards, instead of a few times 10 to the 16 for the microwave standards with cesium. So that means that we have, again, a technology that is over 100 times better than the definition itself allows us to achieve. So guess what? We're going to have to change the definition. And I'm serving on a committee in which we're trying to figure out what that definition will be. And stay tuned, because sometime in the next, certainly in less than a decade, we will redefine what we mean by a second to involve an optical frequency standard. And whether this will be the last change or we will then go to nuclei, measuring the frequency, well, only time will tell. Thanks very much.
We'd like to open the floor for a couple of questions. Go ahead.
And remember, you get prizes. Now, I guess maybe we need to take, yeah, if you can run them, but we need to take the plastic off that. And then, so whoever asks the first question, I'll answer it, and then I'll also say what the prize is. So why don't you handle the questions and I'll answer them. Okay.
Nuclear transition in term 209.
Right, so the question is, what about the nuclear transition? And it's wonderful, except that one of the things that makes it so wonderful is that because the nucleus is so isolated, being, you know, inside all these other electrons, it's not bothered by a lot of the kinds of things. You could put it into a solid and still get a pretty good frequency standard, but not good enough. So we are never going to, it appears at the moment, we are never going to get a thorium nucleus as being the new standard if it's in a solid. But if we take that thorium nucleus and trap it in an ion trap, the way we do any number of other atoms, but use the nuclear transition instead of the atomic transition, that may very well be a good candidate for replacing the best atomic standards that we have now, but it's too far in the future. That is, when we make the decision in a couple of years, it will almost certainly have nothing to do with thorium. That'll be for the next couple of decades. So, okay, so now the prize. You actually get two prizes. So one prize, probably the best one, is the wallet card of the fundamental constants of nature. And one of the and and one of the cool things is the list of constants on the front of this card are all exact. They have no uncertainties because they're the ones that we've used to define the entire SI. So it used to be that there was an uncertainty in Planck's constant, not anymore. So that's one of the prizes. The other prize is the best periodic chart ever made by NIST, of course. And it's got all kinds of good quantum stuff. It's got the electron configurations. It's color-coded according to whether things are naturally occurring, whether they're solids, liquids, or gases. And on the back is a kind of a history of places where NIST has had big contributions to the periodic chart. And there's, at the very top of that set of photographs, is from my own laboratory showing a laser-cooled cloud of sodium atoms. So let's go on.
Questions? Okay, we'll go from the front and work to the back.
Out of the remaining 7, how is the candela like? Sorry.
Yeah, this always comes up, the candela. The candela, for those of you who don't know, tells you what the brightness of a source is as seen by people. So depending on what kind of an audience I'm talking to, I would say the candela is the most human of all of the units, or I might say the candela is the most hated of all of the units because it involves people. Remarkably, people all over the world have very similar visual curves. So basically, the candela is a way of describing how bright something looks to a person, regardless of what its color is. So why do we need it? So you can go to the store and buy a light bulb, and it says how many lumens it's putting out. Lumens and candela are just related by solid angles. So we need something like that. But it's so the candela is defined in terms of how much light is radiated as blackbody radiation from a surface held at a no, that's not how it's done. No, that's an old definition. No, the new definition has to do with the brightness of something at a specific wavelength, a certain intensity, and then you ask people, how does this intensity compare to some other intensity at some other color, and then you integrate over the visual spectrum and. But it's still, basically what it's doing is it's defining the ratio between watts per meter squared at a certain wavelength and candelas or lumens. So that's the way the definition is. So in a certain sense, it's done by fixing the value of a natural constant, but it's not a very fundamental constant. It's a very human constant.
Standard was an actual candle.
That's right. So the original idea of the candle was but a candle, was it tallow? Was it paraffin? How thick was the wick? And there were things that were defined so that you could make these standard candles.
Yeah. So the time measurements, for instance, there's always the precision keeps on improving. Fundamental balance that no matter what you do, it's never going to get better than that practically.
Yeah. So is there a fundamental limit to how good an atomic clock can get? And the answer is, I don't think so. But the amount of effort required to make the clocks better and better always gets quite high when you get to better and better. So let me give you an idea of how hard it's going to be to get much better than where we are right now at part 10 to the 18, which we're not. When we redefine it, we'll have a definition that can be realized to a part 10 to the 18, but it's going to be really hard to do better. Here's one of the reasons why. General relativity tells us that a clock will run slower if it's deeper in a gravitational potential. When I first came to NIST in 1978, the best clocks were in Boulder, Colorado, and part of our NIST laboratories there. They were good to a part in 10 to the 13. That means that if you'd had a similar clock in at sea level, or near where NIST in Gaithersburg is, it would be just barely beyond the level of detectability to see the difference between that clock and the clock in Boulder, which is about a kilometer and a half high. Okay, that would a kilometer and a half would correspond to 1.5 parts in 10 to the 13, which if you had 2 part in 10 to the 13 clocks, that would be just at the 1 sigma limit between them, right? Today, the distance in height that you can measure with these clocks is like that, less than a centimeter. Part in 10 to the 18 is a centimeter. So if we're going to have a standard, today the standard, I didn't tell you that, but today the standard of what constitutes a second imagines that the clock is at a kind of a gravitational equipotential corresponding to mean sea level. Sea level's changing every year. So the ability to even define what we mean by a second is really problematic even now. Now, if you're in the same laboratory and you're measuring 2 things, then I don't have to worry about that. And a lot of the experiments that we do are of that nature. So for example, we now know that the fine structure constant doesn't change by as much as a part in 10 to the 18 per year by having 2 atomic clocks sitting next to each other and measuring their frequencies, and their frequency ratios don't change. And if the dependence of the frequency on the fine structure constant is vastly different for the 2 clocks, which you can find such clocks, then that's an important thing that doesn't require you to know where the clock is relative to the gravitational potential. And it looks like people have got those things down at the 10 to the minus 20 level now. So, the Doppler shift corresponding to the creep of the cables as the temperature changes comes in as a really important feature. But people have ways of getting rid of that. So whatever number you seem to be, there's somebody clever enough to figure out how to go to the next step. So there doesn't seem to be any fundamental reason. It's just that it gets harder and harder.
Yeah, any news on the possibility of the changes in these constants from the beginning of time?
Yeah. Right. Well, so I've told you that year to year, at least the fine structure constant doesn't seem to be changing. But you're wondering about since the beginning of the universe. So there are some experiments in which people have looked at spectral lines from distant galaxies. And when these things first came out, they were looking in the southern hemisphere, and it looked like when you looked back, there was a change in the fine structure constant if you looked back far enough. Not in a way that made any sense, but then they did some northern hemisphere things, and they got very different results. So then they said, well, maybe what it is that the fine structure constant is changing in both space and time, without any good reason. Of course, I mean, that doesn't mean you shouldn't check it, because this is how we learn about new physics. But I would say that most people are not convinced that over cosmological time that the fine structure constant is changing. And if it did change, I would expect it to change mostly in the early universe, where it would have something to do with, say, the total gravitational density or something like that, rather than the difference between 1 and 2 billion years after the Big Bang. I doubt that that's the time scale on which we're going to see things change. So the answer is it's still an open question.
Want to know that from your point of view, what is physics?
What is physics? Okay, well that's not an easy question to answer. And one sort of flip answer is it's everything that's not chemistry and biology, theology. I mean, if you were to, I mean, obviously I'm not going to have a very good answer, but if you look up in a in a textbook of introductory physics, it usually says something about how physics is the study of matter and energy. But the trouble is, everything is the study of matter and energy. So now I saw that you've got pictures of Art Shallow on the wall in various places. Art was a wonderful friend and a real inspiration to me. Art said that a diatomic molecule is one that has one too many atoms. So I would say that when you've got, Art's definition of physics would say that if you've got more than one atom, it's chemistry. Now that doesn't mean it's bad, it just means that it's not what he wanted, I think. I mean, I'm projecting sort of guessing what Art might say. And by that definition, we've done some interesting chemistry in our lab where we've put atoms together at such amazingly long distances that we don't have to think about chemistry, that we can just think about the atomic properties of the atoms to think about the kinds of molecules that they make. And that's been really exciting. So that line, look, I'm sure in the physics department here, you got people who were trained as electrical engineers. And there are probably people in the electrical engineering department who were trained as physicists. So the line between physics and those other disciplines is something that's constantly blurred, and that's a good thing. I think that getting people who have been trained as physicists and people who've been trained as electrical engineers together to work on the same problem can often lead to solutions that never would have been found if those individual disciplines. And you've mentioned how important diversity of perspective is in your own research. I've heard you talk about this, and I really believe it. I think that diversity is a wonderful way of attacking hard problems because you bring different perspectives. Indeed.
It turns out all of the physicists and electrical engineering faculty at CREOL have seen the light.
And how could you not when you're at CREOL?
Hi, I have a question relating to, we just mentioned atomic structure. You showed the plot where there are different experiments ran with different atoms and they have different noise levels. The electron configuration, of course, is going to affect where the transitions are, the number that we have, and there seems to be this preference for alkali metals. But does the choice of atom affect the uncertainty, or can we pin down one atom and it gets the rest?
Well, yeah, the choice of atom does does affect the uncertainty. One of the reasons why alkalis are favored is because they're easy to laser cool. So in order to make this work, you got to have something that's easy to laser cool, but you want other things that are much more subtle, like how sensitive is the atomic transition to the ambient temperature? Why is that a thing? Because blackbody radiation changes with temperature, and the coefficient, how much that shifts depends on the details of where the energy levels are. So for some atoms, you've got energy levels below and energy levels above where things cancel out, and they're not very sensitive to black body. And it's just, the luck of the draw. So people are measuring all these things. So that's one thing that people worry about. And in the end, the choice that we make as to what atom will be the one that replaces cesium is going to be based on things like that. But other things are important too, like how easy is it to make a laser that I can lock to the optical transition. So things like that are going to affect how well you can make all the measurements that are needed to evaluate the uncertainty. So, and one of the possibilities is we don't fix on a single atom. We fix on a basket of transitions. And then as the uncertainties change, we do something.
How about capital G, universal
Yeah.
validation, because in order to do corrections to general relativity.
Right. So the corrections that we make to general relativity don't require that we know what big G is. They require that we know what little g is and that we know how it varies over large distances. We don't need to know what big G is because it's the product of big G and the masses that determine what the potentials are. So now, but since you brought it up, big G is in many respects an embarrassment because it is the least well known of the fundamental constants, and it has historically had a very scandalous career in that people have reported values with uncertainties that are different by 20 times the uncertainty. So that means that somebody, maybe everybody, doesn't know how to make these measurements of big G. And the fact is we haven't really progressed a whole lot since Cavendish in how to measure big G. So, and big G is essentially uncoupled from all of the other constants. So you've got nothing to get to it indirectly. So, so yeah, big G is a real problem.
I think this might be our last question. Have to take just to kind of keep the schedule minimal. Go ahead, sir. Do you think you could always be stuck with material for finding the time?
Yeah. Yeah, so the ideal thing would be that we would define the second by defining the value of a fundamental constant rather than defining the frequency of a transition. The obvious fundamental constant would be the Rydberg. Now, the trouble is that we don't understand hydrogen well enough by many orders of magnitude to use a fixed value of the Rydberg as a way of getting to frequency standards that are good to a part in 10 to the 18. Not even a part in 10 to the 16. So maybe a part in 10 to the 12 at the moment. So, so even though that's appealing from a philosophical point of view, we're a long way away from being able to do that. And if you look at what the possibilities are, you see, we don't know what the proton is like. So one way of avoiding that is look at transitions between very highly excited electronic states called Rydberg states that have the maximum amount of angular momentum, so they hardly ever see the nucleus, and look at those things. The trouble is those high states are extremely sensitive to electric and magnetic fields. So it just looks really hard. So nobody's seriously looking at that.
Let's thank Dr. Phillips.